Okay, so today we're going to talk about colorimetric drug analysis, and we'll get into some interesting things. And I always go out like the morning of lecture and look for new stuff. And so I found a pretty interesting paper on some what they call designer drugs, if you will. So let's jump in. One thing I wanted to do, though, this isn't related to drug testing, but it's related to clandestine drug synthesis. And this is evidence, and I put this up front so that sort of it's emphasized. If you're ever at a tank exchange, and it shouldn't happen at a tank exchange, because the whole purpose of a tank exchange is that they take your tank and they inspect it, and they pull it out of service if it's expired or what have you, and they put fresh tanks back in. But if you see a blue valve like this, don't take it home. Call somebody, get them involved, because this tank has been used to hold ammonia gas for clandestine drug synthesis. And ammonia and brass are not compatible. So the inside of that brass valve could be severely eroded, and it could be very dangerous. So if you go to open the tank or close the tank, you could break that valve off and release all the propane, assuming it has propane in it. It probably does if you're getting it at a tank exchange. But if you ever see this blue color on anything brass, it's probably been used in the service of ammonia. Okay, and so these are different aqueous ions, and the reason it's the aqueous color is because everything is moist in this humid air, and so it makes this moist copper. That's the copper from the brass being leached out, and it makes this compound, and this is a color change. So we can see that brass turn blue when it's impacted by ammonia molecules. We'll get into the clandestine drug, like chemical evidence and physical evidence later. But on the color change thing, I just wanted to highlight that this is a dangerous situation, and you need to not take that tank. Okay. So let's think about how we classify drugs. Colorimetry and precipitation, these are ancient methods, but they have a long history. And so we like to use things that have a general use and accepted history. And so these are still used. They're the lowest sort of on the criterion of determining that a particular piece of evidence is a controlled substance. They're the lowest in terms of the acceptability or hierarchy of methods, but they're still used. Now, if we were to classify drugs by functional groups, that's way too complex. And you can check this out by seeing the drug flashcards or looking at some of the compounds that we talk about today. In other words, when we were studying organic nomenclature, everything was really easy, even though you probably thought it was hard, right? But we gave you one functional group at a time. This is an amine. This is a carboxylic acid. This is an aldehyde. And you start combining all of those. Now, which one do you use to name the molecule, right? So the naming by functional group is great when you have, like acetone, right? Dimethyl ketone or something like that, or 2-propanone. It's very simple to just focus on one functional group and use that in the name. But when you get into these controlled substances or the very strange organic molecules that make up these drugs, it's way too complex. We could use acid, base, and neutral classifications, and this is most common because of the extraction methods used. So we have basic drugs and acidic drugs and neutral drugs. Okay, we'll get into the other secondary classifications, like what they do, like you might have hallucinogens, depressants, stimulants, and then Schedule 1 drugs, Schedule 2 drugs, so the way they're treated in the legal system. So those are other kinds of classifications that aren't really tied to, well, the effect is tied to the substance, but the schedule really isn't. It's just a legal definition. And then we'll focus on the chemistry in this class because the analytical methods are, just volumes and volumes of analytical methods. And so we really can't do a survey of the different analytical methods. We'll talk on the general classifications or types of techniques like today, the colorimetric techniques, but there's just whole volumes of analytical methods. And you can go in and you can type in, even on our search engine here on campus, this is at the Newton Gresham Library, type in forensic analytical techniques and you get a huge long hit list. And you can go in there and search if you're curious. So here's some examples of of neutral, basic, and alkaloid synthetic compounds. I mean, you can come in here and you can see there's an acid group here, but it's also an alcohol, and it's also an aromatic compound. So if you're trying to classify this based on its functional groups, you know, it gets pretty difficult. Now, this one will be fairly easy to name, but try naming morphine by its IUPAC methods. Okay, you've got fused rings, you've got a tertiary amine here, you got some alcohol groups, and then you got this bridging oxygen. So yeah, there's no way I would not be able to do it. I might be able to take a scientific or IUPAC name of this molecule and figure out how they came up with it, but I couldn't start from scratch and give you the IUPAC name for morphine. So what I want you to do for the drug flashcards is to be able to identify morphine and heroin and codeine and so on, but also to know that anything with these three rings like this and this amine group, that's an opiate. And so I really want you to be able to recognize, there's like 4 specific opiates that I would like you to recognize from those drug flashcards. Anything that has this shape is a cannabinoid. Do y'all recognize that? You've seen it enough? I mean, it's even on the little banners that you see in town now. They're putting the chemical structure on there. So, and then this structure here is indicative of cocaine and cocaine metabolites. So this is actually a metabolite of cocaine. So that's that tropane ring. Where do all of these really strange molecular substances come from? These would be a real pain to start with the lab synthesis, try to build these compounds in the lab. These are made in the chemical factories called plants. Okay, it's really strange. Plants don't poop. That's a funny phrase that a friend of mine came up with. She said the reason compounds in plants are so complex is they don't poop. So they have all of these waste products and they try to figure out a use for them. Okay, they try to store them or put them in some sort of excretion. And so these really strange substances. I mean, plants are incredible chemical factories, and there's a whole area of synthetic chemistry called natural synthesis that uses this. They'll use plants, algae, living systems to produce chemicals and then extract them. And they can do things with their enzymes that would take it would be really tricky to do in the lab with just glassware. Okay, let's look at some of the structural ways of putting these structures together. This is a poster that we did several years ago. We simulated the Raman spectra of fentanyl and fentanyl analogs, so-called phentalogs. And this was how Madison in the forensic science department, she put the structure together. And I want you to be able to take this kind of structural diagram because you'll see this in papers. And it's a simplified way to build the structures. And so let's practice. Let's take this and see if we can build some of these down here. Let's start by building fentanyl. So this is the base structure here. So I'm going to go ahead and draw it over here so you can do this in your notes too. Okay, so there's our base structure, and you see the R1, R2, and R3. So the R1, this is color-coded. So fentanyl is black. See this black color here. So we're going to use this piece right here. And we're going to come out. We're going to do the double bond to oxygen here, and then go up and over. Okay. So it's a ketone with an ethyl group on the end. If you had a methyl group on the end, that would be acetylfentanyl. Okay. If you had this, it would be, let's see, the purple one, butyrylphenol. Okay. And then this R3 group, so R3 for fentanyl, you use the black one. And so that would just be an H there. So we really don't have to draw the line, it'd just be an H. And then the R2 group. So for fentanyl, we have this ethyl group with a phenol on the end. So we come down, we go over, we come down. Okay, so there's fentanyl. So do you see how it works? You just R1, R2, R3, use the color code. Now, if you don't have enough colors for everything, you use the black one. So the black one is the default. These are all fentanyl analogs, and so the fentanyl is the default. And so R2 would be black for all of them except for norfentanyl. So this would be the only one that would have the hydrogen. You see how by default, okay. And then all the R3s would be the hydrogen except for this pink one. And then the pink one would use a methyl group. Okay. All right. So that's, if you're confident in that, we can move on. Any questions on this? Yes. And the names? No, but you should be able to do this. So what I just did, you should be able to do. Yeah, with the color coding and everything. Basically this slide, if I were to ask you to do this, could you put it together? Yeah. Okay, so homework and potential test question. Can you use the general figure to draw the structure of all the analogs? Okay, so color tests, these are still used to determine or do a presumptive test for controlled substances. And it uses visual examination. And of course, if you're going to see it in the forensics lab, you need to take a picture of it because that becomes evidence. Microscopes need to be equipped with cameras too so that you can capture what you see. These are called presumptive tests. So you're presuming that, let's say you do a test for cocaine and you get the correct color change, you're presuming that that substance contains cocaine. Then you need to follow that up with a confirmatory test. So an FTIR, a GCMS, something like that, that would confirm that is cocaine, in fact. So these are called screening tests. A lot of these are done in the field. So you can they're portable. You can do spot tests in the field. Most of them are colorimetric. So here's 4 different types of tests. They're always coming up with new tests. And I have some new slides in here that talk about a test for cathinones from the cat plant. Okay. And so these must be followed up by confirmatory tests. GC, LC, FTIR each count as 1 confirmatory test, but when you have a hyphenated technique, it can count as 2. So GCMS, you get the retention time from GC and you get the mass spec. So that counts as 2 confirmations of the substance. Okay, so this is new. I went out and looked for some color test articles, and this morning this one came up. And so this is a color spot test as a presumptive tool for detecting synthetic cathinones. So these are things that give you a sort of a marijuana-like effect, but they're not marijuana. So you can still have your drug, and then you're not, charged for possession of large amounts of marijuana. You've got this synthetic cathinones. And so this is, the forensic community scrambling to try to figure out a good way to test for these and then put them into law. So here's the color change that we see for this particular colorimetric test that they developed. So it goes from clear, you take an extract from the either the powder or the plant, and you can see in the extract when you add the test reagent that you get a color change. So this is what we're talking about in terms of spot tests or color tests. You have these little ceramic plates, typically have 12 little bowls in them, 12 little wells, and you can do lots of different tests on them. So the benefits of colorimetric spot testing is your eye is very sensitive to color changes. If you were to look at the difference I did this with the pH test. So I had brome cresol green, and I can't remember which color is basic. But anyway, you've got an acidic solution. Let's say it's yellow in acid and it turns green in base. And if you take a UV spectrum or a visible spectrum of that, it's hard to tell that spectrum is any different. And yet the color is really dramatically different from yellow to green. But if you look at this spectrum, there's only a small change in the middle of the spectrum where it's green. And all of a sudden, if that absorbance goes up, then it's a yellow compound. If that absorbance goes down, you get those green photons and it's a green compound. So very small pH change, very small change in the spectrum, and your eye sees this dramatic change in color. So your eye is a super sensitive color detector. Now, this is the trick with color tests, and this is probably one of the main points today. Accuracy improves with experience. And so the corollary is that inexperience can yield very inaccurate results. So you really, when you go into if you're going to a forensic lab, when you're doing color tests, you really need to train with somebody, and they can tell you exactly their technique. They can tell you exactly how to read the colors, tell you exactly what to compare it to. Sometimes you have color cards. It's very difficult with just text descriptions of the color, what you're supposed to see. In particular, the test results can change or fade over time because of the destruction of the analyte by the test solution. Some of these have strong acids and bases that will consume or destroy the colored compound. And so even time can be a factor. Must read after 30 seconds. You know, if you let it sit for 5 minutes because you got distracted and you come back, the whole test is invalid. You've got to read it and follow the procedures. And it's also easily adapted as a TLC spot developer. So you can do a thin layer chromatography separation, and then you can spray the test reagent onto the results. Now, we tried this with wipes. We tried to make an oxidizer detector because I knew that the iodine starch reaction would easily detect oxidizing substances. And so we sprayed iodide reagent onto starch, and if an oxidizer comes and steals that electron, it becomes iodine, and then iodine in starch turns black. So we tested this on wipes that were used for detecting in the airports when they wipe your luggage and wipe your shoes and everything like that. They're wiping for explosive residue, putting it into the IMS, looking for explosives. But what if you were just completely covered in potassium chlorate or potassium permanganate or potassium perchlorate? You know, that's suspicious too. You're not supposed to take strongly oxidizing substances onto a plane. Now, they're not technically explosive, but they might be a combination explosive. That might be the oxidizer, and you put it with something in a binary explosive mixture on board. That's why we can't take large amounts of liquid on board, because you can take part A and part B, mix them together, and now you have a hypergolic compound, and maybe even something that could detonate. So I wanted to see if we could come up with a wipe treatment that we could treat their little IMS wipes. And so if they wipe your luggage and the wipe turns black, we got a problem. We don't even need any instruments, okay? And it was successful in the lab with liquid oxidizing reagents. So we could wipe it down, and then we could take the wipe that had the iodine starch on it, and we could spray it with a solution of like perchlorate, and it would turn black. It was very, very sensitive. But dry, we needed a reagent. Doing it dry, like wiping a surface that was contaminated with the same amount of perchlorate, we wouldn't get a color change, because we need mobility. We need a solvent to get the reaction to go. So in a sense, that was a paper that failed. You know, our research test failed. It wasn't useful for dry detection, but it was useful for wet detection. But they're not going to hopefully spray your luggage down with with water so that they can detect it, and it just slow things down. So they wanted the test to be active in 6 seconds too. So there was a time thing. They had to wipe your luggage without, in 6 seconds they needed to see a color change for it to be useful in air travel. It's pretty fast. So here's some pictures from that paper that and I'm going to post this to Blackboard so you can have the original paper. So here's the top one are positive results, and the bottom one are negative results. So the top one had cathinones, the bottom one had other kinds of substances that were not cathinones, and so you got negatives. And then this would be the description that you see in the paper. And notice it's, yellow orange. Okay, that does kind of match, and they sort of tried to make the table look like the color change. Yellow, light yellow orange. I think that's probably this one. This one's yellow here. And then light orange with a green ring around the edges. See how specific they had to get. And that's a pretty good description of that. The color doesn't quite match, but. And then down here, which of these is which? I mean, they've got 8 possible negative color changes. I only saw 4 in the paper. But we have a bright blue. I would call that the bright blue one. This one might be the light green. It's hard to say. But this one is tricky because I might have called that one a positive result. Which one of these is it? Is it the brown yellow? This has got specks in it. And so this is what I'm talking about. It's difficult to know if that's a negative or a positive result because it looks orange to me. And so I would probably call that a positive, and I'd be incorrect. So that's why it takes experience. You got to learn from somebody who's done this analysis or developed it. Now let's talk about the different color shift, spectral shift terminology. You've heard of red shift, right? So this bathochromic shift will be a red shift. I don't know how to come up with ways for you to memorize these. The way I memorize it is I like warm baths, and red is a warm color. Okay, I don't take baths a lot, but if I was going to take a bath, I'd want it to be a warm bath, right? And so, to me, bathochromic and red go together. The blue shift, hypsochromic. That's a crazy one, isn't it? And then hyper and hypo, so it's more strongly colored. Again, it's hypercolored, hyperchromic. And then if it's more weakly colored, if the peak decreases over time, that would be a hypochromic shift. So those are pretty straightforward. Again, stronger peaks are going to lead to stronger colors. And even if something is completely black, that's a strong color, right? The color just happens to be black. Okay, it's taken away all of the wavelengths of light. So you'll come across these terms in various papers, and I want you to be familiar with what they mean. Now let's talk shortly about the difference between a pigment and a dye. Now this isn't so much important for the color test, but it is a place where we're introducing the term dye. And so when we're talking about dyes, a dye is something that's soluble in the matrix, and a pigment is something that is insoluble in the matrix, and sometimes it's suspended. So these would be small particles suspended in the matrix, whereas a dye would be completely soluble at a molecular level. And so this isn't so important for spot tests, but it's important for paint and ink analysis. And so here's 4 families of dyes and then metal coordination compounds. So when you put this metal into an aqueous solution, and it has different ligands around it. These ligands can change the color of that metal. They change the splitting of the d orbitals in those metals. And so that's what gives us a different position of a peak position in the visible spectrum. So this was the ancient way of making colored compounds, like pottery and clay. They would go and find various colored dirts. If you go to Paladuro Canyon or the Grand Canyon, but Paladuro Canyon, you can actually walk around wherever you want. It's really great. You'll see purple soil, orange soil, yellow soil. You see all these different colors. And so if you wanted to make purple pottery, you would go over to that part of the mountain and scrape a bunch of that clay off and mix it in with your clay and make a different color. So those are metal substances. It's also how we tell if something's really ancient or if it's fake. If you're looking at a pottery glaze and you're able to detect the colored compound and it has some sort of organic chemistry that took place, it's not ancient, right? All the ancient colored compounds were metal based. So the modern ones have these 4 families of dyes that we're going to look at next. So here's the terminology. And again, these are 4 families of dyes, but some of the compounds kind of overlap. They'll be in 2 categories. And so you got to have some play in the joints, okay? Don't be so rigid to say, well, which is it? Sometimes it has a carbonyl and sometimes it has an azo in it. So it's a combination of the 2. But this may be a new term for you, this triarylmethine. So this one, let's focus on that one first. What's this methine piece? Well, methane is a single carbon, right? What's methine? Well, it's a carbon bonded to 3 things. So this is the methine piece right here. And with resonance structures, you can see how that's a planar carbon, but trigonal planar. But you could also take that electron away and make it positive. So a lot of times this will be a cation. So you're looking for a carbon with 3 bonds and a plus, or a carbon with 3 bonds like this. So whenever you see those, you know it's a methine dye. And what makes it colored a lot of times is when it has aromatic rings around it. So the aryl part is what gives it the color. Now think about why something is colored. It's colored because it absorbs in the visible region of the spectrum. So this particular chromophore has peaks that hit the visible region. Okay. Without the aryls, it's going to be colorless. But if you extend the pi cloud out to those aromatic rings, then you're getting the homo-lumo gap down into the region where the visible spectrum absorbs. So that's what makes it a dye or a colored compound. Any questions about this type? Okay. What if there's only 2 of those aromatic things? It could still be colored, and it would be diaryl methine. So you're looking for those 2. Okay. Now, acetone's a carbonyl, okay, and it's not colored. So it's not just carbonyls that make colored chromophores. It's carbonyls on extended pi systems, but those aren't in the name. So. And those of you that had PChem for me, and I think also Dr. Skargard, whenever you talk about the particle in a box, right, as you extend the box, the difference in energy levels drops, and that's what's happening. When we extend that pi cloud, the homo-lumo gap drops, and then you get peaks in the visible spectrum. All of these would absorb in the UV if they were smaller, but then as you extend that pi system, now those gaps get into the visible range and you get a colored substance. Now, what's the carbonyl thing? Well, the carbonyl gives you these lone pairs of electrons that can donate into that extended pi cloud. So a lot of times it's not the homo-lumo gap, there's an N, a non-bonded electron to the LUMO gap. So this, it's still a molecular orbital, but we call it N to pi star or something like that. These also, whenever you can take these systems and join them together, you can extend that pi system, and then you have this carbonyl. So if you see these kinds of systems with a carbonyl stuck on an extended pi system, you got a carbonyl type dye. Okay, nitros are really easy to identify. You see the nitro groups here. And again, you need that, it's typically you need that extended pi system. So instead of the carbonyl, you're just taking some of these non-bonded electrons in the nitro group and bonding and sending them over to this extended pi system. So I'm going to go ahead and draw an arrow down here for this one too. So nitro is easy to find. This is a sulfonate group. So it's like not a carboxylic acid, but it's an acid with the sulfur group on it. And a lot of the dyes, like commercial dyes, food coloring, and so on, have those groups on them so that you can make the organic substance soluble in water. So they don't really do much to the spectrum. They just make it more soluble in water. Because you want your food coloring to be soluble in water. And then over here, these are azo dyes. And so this is the azo linkage. We have those non-bonded electrons, and that's the azo group. This is an unusual way to draw it because most of these are trans. This one is cis. So most of the azo linkages are going to be like this. And light comes in and it takes those non-bonded electrons and dumps them up into the anti-bonding orbital. So the azo group, which is the double bond is my thumbs, okay? Let me do it like this. They go to the anti-bonding, and then this is now a sigma bond, and it can spin. So the rods and cones in your eye use rhodopsin, and that's the light detection molecule in your eye. So you get this excited state that can spin, and it rotates, and then that tickles the nerve and sends a signal to your brain, and then it drops back down into the double bonded flat azo. Okay. So let's look at the various spot test reagents and see if we can identify which kind of class of dyes the coloring agent is. So here's methamphetamine and amphetamine detection using the Marquis reagent. And so it doesn't get into what the Marquis reagent is, it just shows what it does. And so here's cold medicine, amphetamine, here's methamphetamine. You see this methyl group stuck on the nitrogen. And this is a controlled substance. Totally similar molecules, okay? And so if we react cold medicine with the Marquis reagent, what's produced? Do you see this right here? What do we call this little piece? That's the methine piece, and this is the aryls. There's two of those. So this is a diarylmethine. And the absence of this methyl right here and here causes it to be an orange-red color that fades to brown. And so if you did this test, you would say, wow, it may be an amphetamine-related molecule, but it's not methamphetamine. Whereas if you do it on methamphetamine, you see an orange color, persistent orange color. So orange-red versus orange, I want that person to have some training so that they don't take the cold medicine out of my backpack and think that it's methamphetamine, right? So that's what we're seeing. That's a diarylmethine type of dye. Okay, here's the same reagent, the Marquis reagent, testing for morphine. So if you look at the scheme, it's in the textbook. It was pretty tricky to look and say, what's going on here? Well, I've circled the active places. So this Marquis reagent with formaldehyde comes in and it takes this spot of the molecule here and bonds it together and makes a dimer. So this is a dimerization. The previous reaction also was a dimerization. And so what do we end up with? And this text is new. So if you have your notes, this text is new. This is, again, what type of dye? Well, it does have in the middle of this little methine piece, but I think this is probably more accurately classified as a carbonyl on an extended pi system. So this is a carbonyl, and there's a bunch of them on here, and this is the extended pi system. But it benefits from both. You could twist my arm and say it's a diarylmethine. You could also convince me that it's a carbonyl on an extended pi system. But you're not going to convince me that it's an azo, right? And you're not going to convince me that it's a nitro. There's no nitros in this molecule. There's no azos in this molecule. So there are clearly wrong answers, but there are two possible right answers. If I were to ask you what type of dye molecule this is or what kind of colorant it is, you could say it's a triarylmethine or diarylmethine, because there's only two of those aryl pieces on the methine. But you could also say it's a carbonyl on an extended pi system. Does that make sense? Okay, good. I see some nods. Okay, let's look at Ehrlich's test with this p-dimethylaminobenzoaldehyde. Okay, so we react this. Now, this is an interesting thing too. I want to show you this is the molecule LSD, pretty complicated molecule, and the textbook uses some kind of a common technique where we want to just eliminate part of the molecule because it's just going to confuse the drawing. We're just going to focus on where the chemistry takes place. And so do you see this little dashed line, this little wavy line? You know, if you come into the middle of this diagram, you're like, what is this little wavy line? You know, is that a aliphatic hydrocarbon chain? You know, is that meant to be CH2 groups? No, it's just sort of saying there's more to this molecule. Okay, so you got to back up in the drawing until you find where the more of the molecule is. We do the same thing with R groups, but this is just a much more complicated R group. So reacts with the reagent, PDMAB, and you get a dimerization. You get a dimerization here. Actually, they attach to each other here. And then you react it again, and it creates this triaromethine piece. So here the carbon still has 4 bonds on it, but then that hydrogen is easily removed, and you've got the methine group here, and then the 3 aromatic pieces, 1, 2, and 3. So that's a triaromethine type dye. We could react phenols and amines via the Lieberman test. And this uses p-nitrosophenol. Again, so this nitroso, this is the nitroso piece, and it'll react with this bottom carbon on a phenol group, and it will start linking this chain together. And so we end up with, again, a carbonyl on an extended pi system. So this is a carbonyl type dye. We could also detect methamphetamine using the Simon test. And this one uses the coordination compounds, the metal. So here's a metal surrounded by 6 ligands. It's going to react with this, with the nitrogen piece here, and it's going to form this metal complex. So this metal coordination complex is going to give us a blue color. Now here's marijuana via the Duquesnoy-Levine test, and you've got this. You take the extract, so you crush the leaves or buds or whatever it is, the plant material, and extract it with petroleum ether. Okay. Then you add the reagent to the ether, and you look for a color change, and then you add hydrochloric acid and look for a color change, and then you put in an addition of chloroform, and you get a different layer, and you look for preference to the different layers. So there's lots of color changes you can get. There's lots of cannabinoids, and so you're going to get lots of different results based upon the different types of cannabinoids that you have. Okay. This one is really good for using as a developer on a thin layer chromatography base. So you can take that ether extract, put a dot of that substance on a thin layer chromatography, elute it, and you get separation, and then you can spray it with that fast blue detector, and you'll see the different compounds show up. Now this produces an azo linkage, and I want to show you this kind of strange way of drawing this connection. Okay, what do you think they mean? That azo is being shown to be attached to the very center of an aromatic ring. That's weird, isn't it? Have you ever seen that before? We didn't do that in organic textbooks. So how would we interpret that? There's no atom in the middle of that ring to bond to, so it can't be bonded to the middle of the ring. No, and that's another thing. They commonly just don't show the lone pairs on these structures. Yeah. And so there's lone pairs on the oxygens and lone pairs on those nitrogens, even though they're not shown. This is showing you that it's bonded to that 3-ring piece of a cannabinoid, but it's leaving it uncertain as to which carbon atom it's attached to. So that's really all it's saying. Is it's saying it could be attached to here, it could be attached to there. These other things on these other carbon atoms, so it's not either one of those. Okay. Unless it breaks the aromaticity, it might attach there and break the aromaticity. So let's talk about colorimetry and how we describe the colors. So at the sort of the freshman or maybe even middle school and high school level, when you're just learning science, they start talking about corresponding colors. So if something absorbs in the yellow, it'll look purple, and if something absorbs in the purple, it will look yellow. So this is the color wheel analysis, or way to describe color, and they'll use things like lambda max, right? So if lambda max, let's say, is equal to 420 nanometers, then it's a yellow compound. And that's pretty accurate if you just have one peak. So if you've got a spectrum, a visible spectrum, and you see just one peak down in the blue region, that's going to be a yellow compound. Okay. But what if you have multiple peaks? Okay, some of these things have multiple peaks. How do you know what the spectrum is? You can go back to PChem and do the color lab, the RGB color lab, and that'd be a great way to do it. But you said it was pretty tedious, wasn't it? Okay. What if you had asymmetric peaks? What if you had strongly colored substances or powdered substances? And so is this description of the color change good enough? You're looking for a yellow-orange substance or a light yellow-orange substance, okay, or brown-yellow. What's the difference between yellow, orange, and brown-yellow? It's really not that much, and it's going to be difficult to know. So these verbal descriptions of color is what led me to doing that whole color lab in PChem. And this was the second paper that we did, and it talked about going beyond just lambda max, okay, in describing different peaks. So you have lambda max is equal, in this case, 550 nanometers, and that is not enough to describe the color. So here, the full width at half maximum is necessary. So this is the, but that's not enough either, because this dashed peak has the same full width at half maximum. What you also need to know is the asymmetry. So how does it tail? That's another way to say it. How? Like in this case, that color is the red peak, the red colored substance, tails to the short wavelength side, so it absorbs the blue wavelengths. Even though its lambda max is at 550, which is in the green region, it's tailing towards the blue, which means it's absorbing the blue and leaving the red untouched. And so you're going to get a red substance. This peak, this dashed one, has exactly the same lambda max, exactly the same full width at half maximum, but it tails towards the red. And so it leaves the blue wavelengths untouched. And so that substance is going to appear blue. So if you're describing something spectroscopically, you have to take into account the asymmetry of the peak. That's the take-home lesson too. So if you're writing a paper or trying to describe your spectroscopic results, do not just give lambda max. That's your take-home lesson. That's not enough information. Tell me how wide the peak is and whether it's asymmetric. Does it tail to the high wavelength side or low wavelength side in absorbance? That will tell me which wavelengths are preferentially absorbed and which ones are passed through the substance. Eventually you get to these descriptions of the color. You can take those XYZ values and convert them to red, green, blue values, RGB values like you did in the lab. You could also convert them to the Munsell system, okay? And this is the Munsell system. So you've got this this Munsell value that goes from 0 to 10. That tells you how, I guess, black and white the compound is. You can have pastel colors, which are still colors, but they're on the white end of that stick. Or you can have really dark colors, which are still colored, but they're down close to the black end of that stick. The chroma is how strongly colored it is. Like if you have a 0 chroma, it's just a gray. It's different levels of gray. But if it's way out here, the chroma value, like at 12, see how bright that blue is. And then the hue is this angle around the circle. And so there they're giving still sort of verbal descriptions of these substances. Yellow, GY is green yellow, okay, G is green, and BG is blue green, BP or PB is blue purple or purple blue. You've got red purple and red yellow. So you've got all of these different combinations, and you can see the colors there. And so here, if we're doing the Ducanol-Levine test on THC, the extracting solvent is ethanol, we should get this range of colors: a 7.5 purple blue, a 7.5 purple. So you can get purple and purple blue. But what if it wasn't THC? What if it was tea? You don't want to get somebody in trouble if they just got loose tea in their backpack, right? And I nearly ran across this. I did not get pulled over, but I thought later, I was like, oh my gosh, I'm so glad I didn't. I had a cat in college, and my buddy had a cat, and we were at pet store running around, and they had catnip. I was like, have you ever given your cat catnip? And he said, no. I've heard it's great. And we didn't have Instagram with all the videos of the cats going, So we just wanted to see it for ourselves. So, but the thing was like a brick of catnip. It was huge. Yeah. And I was like, I don't want that much catnip for my cat. So we bought it and split it. So I put it in a Ziploc bag and threw it in my car. And went weeks. And then I was cleaning out my car every 10 weeks, whether you need it or not, right? And I found this bag full of catnip in my car. I was like, oh my gosh, I'm so glad I didn't get pulled over for rolling a stop sign or something. They'd be like, what's this? And I mean, drug laws were serious in the 90s. Okay, so this wasn't something that would be no big deal. But anyway, hopefully the catnip, which I don't know what catnip would do with these tests, but hopefully it wouldn't be the same as marijuana. So T would come out as green yellow. Well, that's great. So 7.5 purple blue. So where's purple blue? So here's between 5 purple blue and 10 purple blue. So the marijuana would come in with this color, and T would be green yellow at a 5. So 5 green yellow. Pretty easy to tell the difference. Okay. So that's what those little designations mean. That's from the NIJ standard. Here's more for the NIJ standard. We've got, and this is posted. You got hydrocodone, ephedrine, and so on. And then down here you got phenobarbital, mace, nutmeg, and tea and THC. So we can zoom in and see the different things that we see. LSD, mescaline, morphine monohydrate. So yeah, we've got and opium powder, oxycodone, and sugar. That's a good thing to know. So the difference between oxycodone and sugar, let's look at those. So here, oxycodone would come in at 7.5 yellow. So between 5 yellow and 10 yellow, so it would be right in there for oxycodone. And for sugar, it would be 10 yellow. Woo! Not far enough apart for my taste. Okay. So you want to do a different reagent. This is using, let's see. Well, it doesn't say on this one. But you'd have to go in there and say, well, oxycodone and sugar are going to give pretty similar color values. And so let's use a different color test than this one. Now, in that paper I did on the colorimetry, I wanted to look at phenolphthalein, since that's such a common color that we see even in freshman chemistry. And I was able to match the colors pretty well, okay? And the only difference was this rotation of this acid group. So that's enough to cause the shift between clear and colored. So that's pretty amazing. And so it's a short lecture today. That's all I've got for you. Are there any questions about how to classify these dyes or anything related? Let's talk about the control chart too. So go ahead.
I was just going to ask, are you going to want us to memorize the structures for the dyes or just not?
No, not at all. No, just be able to recognize those classes, those functional classes. So let me go back. This is what you need to memorize here in terms of what you're looking for, right? So you're looking for that kind of structure. And so that's why I went through these examples of trying to find, this is the colored substance and classify this. So this is clearly a diarylmethine. And so you would, if you were to say azo for this one, that's clearly wrong. Yeah, so that's what I'm trying to get you, just sort of recognize, not draw for sure or anything like that, but to recognize which kind of dye is this complex. Yeah. So hopefully that makes you relax a little bit, because I mean, there's so many compounds. Look at the drug flashcards. I put up there on Blackboard for you. Okay, so the next week is the first report, the midterm quality report. There should be an example on there. Look at that example. You should write it very closely to that example. Okay, so including like the purpose of the whole exercise. If it's exactly the same, I'm not going to count off on that. That's the purpose of this exercise. What needs to be different is your procedure. And it needs to be detailed, like how, like if you've got a time-based thing, when do you start the timer? When do you end the timer? How do you make sure you don't miss a day? Those kinds of things. Okay. Where do you go to get your information? List the website. Okay. Now you don't have to say, then I go in and type the number into cell number 8 in the column B in Excel. I mean, that's too much. I don't need to know what column in Excel you're typing the number in. But if I were to say, I want to go see the same URL or same, research page you're using, like Yahoo Finance or something, put the URL in there so that I could go check it out too. Okay. If you do anything to the data, if you convert it from hours, minutes, seconds into seconds, describe that, just say, multiply the seconds by 3,600 to get to hours, or I divided the hours or whatever, multiply the hours by 60 to get to minutes, and so on. So then I'm going to assign everybody to review 2 reports, and you're going to learn how to give good reviews, good feedback that people can utilize. And so we used what some people call it the affirmation sandwich. I don't really like that so much, but you give some positive thing that you identified, and then you give some things that are critical input, and then you end with something that you're interested in that really, would make the paper way better. I like because it's easier to remember the roses, thorns, and buds. Okay, have you heard this? We did this in Scouts when we were hiking Philmont, because you're 12 days with a bunch of boys and people are getting on each other's nerves. And so at the end of the day, we'd go around during dinner and say, what was a rose? What was something nice about today? And it sort of reduces the toxicity of the group, right? And so you're going to say, what was nice about this paper that I saw? Maybe they had some good figures. Maybe they did a really, really good job of formatting it. Maybe their technique was interesting. Okay, so you write it was interesting that you did this. And then the thorns. Well, you need to get this proofread, right? Your grammar had a lot of mistakes. You had 2 sentences with no subject, and you're specific about where those are, because your papers are going to have line numbers. So you can say line 57, I couldn't find a subject for this sentence. Or you misspelled, my favorite is misspelling vial. It's VIAL, not VILE. Now that really doesn't apply to this paper, but in PChem reports, I would just laugh so hard because you take a 4 mil VILE. It's not evil, right? It's not vile. It's a VIAL. But so that's not, your spell check's not going to catch that one, because VILE is a word. Okay. And so those would be thorns. Those are things that could be improved, things that, are not good. And then the bud is like, after you make these changes, I think this is going to be a great project because blah, blah, blah. And everything needs to be specific. Don't just be vague. You will actually lose points as a reviewer if you just say, this was great. This was great. This could be better. This was great. And don't give any specifics, right? That's not very useful. If someone just tells you, oh, this paper was great, and they don't have anything specific. What was great about it? I want to make sure I do that every time. If you don't tell me what was great about it specifically here, I can't repeat that, because there's lots of details. Which detail was great and which detail needs to be improved. So that's part of this exercise. So part is writing the midterm quality report, which is a pretty easy assignment because you've got an example. And in this particular case, when you're dealing with reports, standardized reports, those are not creative writing assignments. So I do not want a creative writing assignment where you're trying to sound flowery and grandiose. if you use AI on this, it will stick out like a sore thumb because AI is very grandiose, and once upon a time, I was counting the steps, right? And that's going to really be bad. So don't do that. And then you're going to learn how to give good reviews. And then on the second one, the final quality report, you will respond to each of those reviews from your reviewers. And I'll be testing to see how you responded to those reviews. So that's hopefully gives you an idea. So get started on those this week because it's due next week. So you're not crammed at the end. And get a friend to proofread it. Okay? It's really, really a good practice. I know it's uncomfortable, but find somebody. If you can't find a friend, go over to the writing center and they'll assign one to you. They'll read it for you. They'll give you some feedback on your grammar. But push back on them when they try to get you out of passive voice. It should be third person passive. Okay? So don't use I, don't use we. Talk about, the steps were out of control on such and such day. And they would like you to use active, verbs and so on, because most of the writing that people do is expressive writing. This isn't about expressing yourself. In fact, you want to pull yourself out and just have the data. That's why science is sort of way ahead of this whole, that gets into a political discussion. Science is way ahead. We pull the researcher out so that the researcher's not important. It's the data and the conclusions that are important. And so we've kind of gotten past that's how science has flourished and gone through times of prejudice because we said, let's focus on the data, not on the people doing the work. So, yay science. All right. So I'll see y'all next time.